Welcome to another lesson where we will be discussing our very last theorem for complex numbers. That looks pretty scary, no? Its algebraic proof is a bit tedious. Therefore, we will be proving it geometrically. Wow, there's a lot to catch. Why don't we break it down and discuss every point and line of this diagram before we actually get to the theorem? It all starts when we take two complex numbers, z1 and z2, that were plotted on the Cartesian plane represented by points A and C. Thus, OA and OC are the vector versions of both the complex numbers. This is a perpendicular dropped from point C to x-axis at point M, while this A is representing the horizontal component of vector OA. Anyways, we completed the parallelogram OABC by drawing the parallel vectors and then used the parallelogram law of vector addition to represent both OA and OC by a resultant vector OB. Hence, the coordinates of B are the sum of the coordinates of A and C. Seeing the coordinates, it's easy to tell that this A plus C and B plus D are the horizontal and vertical components of B. Now that we have discussed every point and line of diagram, let's get to business, proving the theorem. Alright, so if A and C are associated with complex numbers z1 and z2, therefore we could see that the complex number represented by point B is the sum of z1 and z2. If that is so, then the modulus of this new complex number is representing OB, or its length in fact, starting from origin and all the way to point B. Similarly, the modulus Z1 is representing length of OA, as you can see on the Argand diagram. And the same goes for Z2 and OC. Not just that, since vector OC is same in length as that of vector AB. Hence, they both are equal to the modulus of Z2. Now, to get to our theorem, let's put all our focus to the triangle OAB. According to the triangle inequality theorem, the sum of the lengths of any two sides of a triangle is greater than the length of third side. Following that, we state that the sum of these two is greater than the third side OB. Now, substitute the value of OA, AB and OB in terms of moduli of the complex numbers and hold it for a while. The same theorem of triangle inequality talks about the difference too. Difference of the lengths of any two sides is less than the length of the third side, and their moduli form looks like this after substitution. We can then combine these two inequalities into one. But this result holds valid only for the inequality, as you can see. But our required form says something else. Well, in order to obtain equality, these points should have been collinear like this. When would that happen? Well, you already know that the collinear point has the equal ratio of their coordinates, right? Thus, in our case, the ratio of the coordinates of point A should be equal to the ratio of the coordinates of point C to get to the collinearity between A, B and C. And if that happens, then the sum of Z1 and Z2 will be equal to this after simplification, where OC is none other than the sum of Z1 and Z2, as you can see in the diagram. Finally, if we compare this result with the one that we had before, we can easily combine them to deduce this form, proving the last theorem of our journey. The modulus of the sum of two complex numbers is less than or equal to the sum of the moduli of the numbers. A little long and tedious, no? But don't worry, after this lesson, you'll be an expert on the modulus, so this won't be a problem for you at all. Overall, great job friends. Proud of the hard work you are putting in. If anything still feels unclear, have a quick look back at the lesson. See you in our next video.